Welcome to day 17 of the advent of compiler optimization. Today we're going to be talking about probably the single most important optimization that the compiler can do, sometimes called the mother of all optimizations, inlining. I'm going to be using the ARM instruction set again today, just for old time's sake more than anything else. And I'm going to start by writing a simple function to switch the case of a string that's been passed in. So let me include some things here. I need CC type, and I need C string probably, C string. And I'm going to write a little utility function first of all. I'm going to say char switch case, and so I'm going to make this function able to both make something uppercase and lowercase configurably. So let's write a little utility function that can deal with this. So we're going to say char C, and then we're going to say bool upper. Okay, so we're going to say if we're switching to uppercase, we are going to say if C is A and C is less than or equal to Z, then what we need to do is we need to do we need to return C minus the A plus the capital A. So that turns the lowercase a into a capital A. Otherwise, if upper was not set, we're going to say if C is greater than or equal to, and this is a terrible way, there's all sorts of other functions to do. Again, I'm writing this on purpose to make it do something hopefully interesting and maybe even entertaining. Whoops, I can't type. Return C minus capital A plus lowercase a. Otherwise, if it's neither of those things, if it's either not falling into either of those ranges, we're just going to return C. So there is our first function call, and you can see it's quite complicated. Let's use this function in another function to actually make the string uppercase. So I'm going to say void to upper. I'm going to take a const char star string, and I'm going to say something like while star stir equals switch case stir comma true. So this is going to make it uppercase. And why is that not working? Oh, because I have to do, first of all, plus plus. Oh no, I'm going to have to do star stir equals switch case star stir, and then separately plus plus stir. Otherwise, I can't do the plus plus. Oh, why can't I do that? Oh, because it's const char. Yeah, char star stir. There we are. We're in place uppercasing something. Hooray! I got it to compile. I can write. So let's take a look. Well, we know that the switch case up here is quite complicated and has a bunch of stuff we won't go into right now, but it makes sense if you read it through. If you pause the video and read through it, it makes a lot of sense. Let's have a look at what happened in our toUpper function. Well, the first thing you might notice is that there's no call instruction. The toUpper has not called switch case. Now, we've already seen evidence of this before. This is inlining. We know that when we looked at the vector's size and the begin and the end of various other bits and pieces that we've seen along the way, that we don't see a call routine. So we kind of take it as read that functions don't always happen. We saw that strlen does get called a few days back, but we're also seeing now that this particular case of switch case has been completely copy-pasted into the implementation of toUpper. And that's what inlining is. Inlining takes the body of a called function and brings it into the place that it is called from. Back in the early days, the overhead of actually calling and returning and pushing and popping registers to stick with ABI was the primary motivating factor for doing inlining. But nowadays, something else happens when we inline a function. We can take advantage of the fact that now we have a unique bespoke copy of that function, and we can specialize it in place for the exact arguments that it's being called with. Let's see what I mean. So our loop here, from lbb1_2 to this other place here, there is no complicated to case. Now, if you look up at the top here, there is actually two different cases of the switch case because there's if upper or if not upper. But when we inlined the routine, when the compiler inlined switch case, it saw that we're always passing true here. And so what it was able to do was effectively copy-paste the set of if statements in here down into line 17. And then it said, well, upper is always true, so I can throw away the other half of the if statement. And so now we've got a bespoke to-upper routine that only does the operations needed to turn a character from lowercase to uppercase. Again, there are much better ways of doing this. There's to-upper and there's all sorts of other bits and pieces. But what I'm trying to show here is that the inlining has not only removed the overhead of calling and returning, it has made a bespoke special case version of that function and is able to apply things like propagating constants, like the fact that upper is true, and doing dead code elimination. Once we know that upper is true, we know that the second half of that else statement will never execute. Inlining is a fantastic optimization that the compiler will do quite often. The compiler has a really difficult job though. It's not always obvious which functions are worth inlining and which ones are not. For example, a big function is probably not worth inlining into a smaller function that's used in many, many places because the code blow-up will be huge, unless that big function dead code eliminates down to something much smaller. So the compiler has to use a whole bunch of heuristics to try and work out which things are profitable to inline and which things are not. And the drawbacks of inlining can be code bloat. The functions grow as more and more functions are pulled into them and their bodies get bigger and bigger and bigger, which can have nasty side effects for your instruction cache. And sometimes, but not often, sometimes having one centralized copy of a single function can allow a branch predictor to learn about the kinds of branches that happen inside that routine. So by pooling all of the times that you call a particular function and then letting the branch predictor see just one copy of it, it can learn a bit better without filling up the branch predictor sort of memory with loads of copies of that function around the code base. So there's loads of things that are competing to try and make the compiler's life difficult here. And so hopefully if you've ever looked at the output of the compiler and gone, why the heck has it not inlined this? Then maybe you'll have a little bit of sympathy for it next time. It's really got to try and read your mind and try and make its best guess. Either way, we're going to look at some more optimization related to inlining tomorrow. I hope to see you then.